Good morning. Good morning.
Morning, sir.
Okay, I start. Ask your friends to join. Okay, we have derived the torsion equation. We will go ahead and look at few design criteria and other related terms. Torsion equation was given by in the form P by G. In the form P by J is equal to tau by R is equal to G pi by L. Okay. There's something called as polar suction modulus. Polar suction modulus indicated by Z. Z. Let me write ZP if you want ZP. Polar suction modulus. It is the ratio of polar moment of inertia. It is the ratio of polar moment of inertia to extreme radial distance of the fiber from the center. It means to say that polar moment of inertia Zp for a cylinder is the ratio of polar moment of inertia, it is J, to the extreme radius. Extreme radius from the center is nothing but Z, that is R radius. If I consider a circular cross section, extreme radius from the center is R, whereas Whereas if I consider a hollow cylinder, the extreme radius I will call it as R naught, inner radius I will call it as Ri. Okay, let me write this. Zp of a solid cylinder, which is nothing but polar moment of inertia, which is nothing J, divided by extreme radius, in this case is R, or also I can write it as J is pi d power 4 by 32 divided by R is d by 2, or d is equal to 2r, or r is equal to d by 2. Or I can write it as pi d power 4 by 32 into 2 by d, or which is equal to pi d cube by 16 is the polar moment of inertia in case of solid cylinder. Polar suction modulus in case of solid cylinder. Polar suction modulus in case of hollow cylinder, it is also J by, in this case this is R naught, J by R naught, which is equal to pi d power 4 minus di power 4 by 32. I have to take the extreme fiber from the center, extreme radial distance from the center, that is nothing but your d naught by 2. You should not take d or di, it is d naught, extreme distance from the center point to the outermost fiber, or pi into d naught power 4 minus di power 4 by 32 into 2 by d naught, or Zp of hollow cylinder, which is equal to pi into d naught power 4 minus di power 4 by 16 d naught. That you should remember. Okay, this polar suction. Why it is important in the sense, uh, higher the polar suction modulus, lesser the twist, lesser the shear stress induced, and higher the torque withstanding capacity, which we will discuss. So this polar section models is very important. Okay. Next, uh, one more thing I want to discuss. When I say torsional strength, torsional strength. Okay, I am talking about my maximum shear strength, my maximum shear strength capacity of the shaft. Torsional shear strength, it is the ratio of torque to the maximum shear stress. These are two terminology. Maximum shear stress. Okay. Torsional strength is nothing but T by tau. Okay. Torsional rigidity. Torsional rigidity. Rigidity in the sense resistance to deformation, or torsional stiffness. It is the ratio of torque. Okay. It is the torque required to produce unit angle of twist. It is T by J is equal to tau by R is equal to G theta by L. Or torque required to produce unit angle of twist, T by theta is equal to Gj by L. Well, T by theta is also called as torsional rigidity, or torsional stiffness is given by Gj by L. Okay. Torsional flexibility. It is the twist. It is inverse of that. The twist produced due to unit torque. Inverse of that, or torsional flexibility is given by theta by T, which is equal to L by Gj. Torque required to produce unit angle of twist, or twist produced to unit torque is a torsional flexibility. Okay. And this T by J, similarly T by tau can be written as J by R. J by R. Okay. Keeping this in mind, we go ahead designing the shafts. Shaft can be designed according to you. According to syllabus, we have two criteria: design of shafts. Design in the sense we are finding dimension. Design in the sense dimension, stress, area of cross section, or material. Everything comes into picture. But whereas here we are determining the dimension, that is diameter. It can be inner diameter, outer diameter, for a solid shaft diameter, length, etc. Design in the sense we are determining these parameters by using two theories. There is strength criterion theory, strength criterion, strength criteria, and the second is the rigidity criteria. I can design my shaft based on two criteria, either strength criteria or rigidity criteria, but I have to check for both. Okay. Strength criteria. What is strength? Strength in the sense shear strength. It is nothing but shear strength tau. How to design now? Therefore, according to strength criteria, what does it says is the permissible shear stress should be should be within within the limit. In order to design this shaft, the permissible shear stress, for example, 150 MPa. My dimension should not, if I design the shaft, my dimension should not exceed 150 MPa. The permissible shear stress should be within the limit. How to do that? T by J, which is equal to tau by R. Okay, this is what R. T by tau, T by tau is equal to T by tau, which is equal to T by J, J by R. Okay, or I can also write in this way also. This is a little confusing for you, but you will understand like this only. Give me a moment. It's audible. It's audible.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. There's some internet issue. Okay, I'll continue. T by tau is equal to J by R. Generally, this is more than sufficient, but for your understanding or curiosity, I'm telling you, this has to be in this way. Tau max. I'm designing for maximum shear stress. Tau max should be equal to TR by J, which is equal to T into D by 2 by J, if I consider solid shaft, which is pi d power 4 by 32, which is nothing but pi d power 4 by 64 plus pi d power 4 by 64, which turns out to be pi d 4 by 32. This will be equal to 16T by pi d cube, tau max, which is equal to 16T by pi d 16T by pi d cube. See, uh, it means to say that when I design my shaft, that is by find torque will be given, tau will be given, my diameter d should be less than tau max. For example, tau max is given as 200 MPa. When I design this shaft, assume that I am doing reverse engineering. This d, when I substitute in this formula, I should get less than this should be some 45 mm. By substituting 45 mm, my tau max should not exceed 200 MPa. That is, this is designing this. Okay. Then if I say diameter d cube, this will be greater than or equal to 16T by pi into pi into tau max. Diameter should be greater than, my diameter should be greater. This is this is the inequality. But when I design it, diameter should be greater than this term. Diameter should be greater. This, for example, if a diameter is equal to 45 mm, my diameter should be greater than 45 mm in order for the shaft to withstand this 200 MPa stress. Okay, this is what generally this is how it should be understood. In the other way it means like this, but when I design it, it means the diameter should be greater than 45 mm, or at least greater than or equal to 45 mm, so that my shaft is capable of withstanding this much torque and this much shear stress. Okay, this is strength, nothing to worry. Only by using this equation we will derive this, we will use the calculate everything. But this is how when you are doing the machine design 1 or 2, this is what we'll use. EQ greater than or less than equal to 16T by pi tau max. A diameter should be at least equal to or greater than this inequality 16T by tau max. By tau max. Next, rigidity criteria. As soon as I say rigidity in your mind, it should be a picture like I'm talking about the deformation. That is theta. Let's talk about strength criteria. I am talking about my shear strength. That is tau rigidity criteria. Let me indicate it as theta. T by J, tau by R, G theta by L. I will take this G theta by L. T by theta is equal to rigidity or torsional stiffness is Gj by L. Or I can write, let me write like this, theta, uh, theta is equal to TL by Gj, TL by Gj, or, or if I write, this will be, this will be equal to TL, TL, G is constant, pi d power 4 by 32, or 32 TL, 32 TL by G into pi d power 4. Okay, therefore my this d power 4 should be at least greater than 32 32 TL 32 TL by pi g theta. Don't worry, will not use this. So when I design the shaft, for example, by using strength criteria, I got 45 mm. I got 45 mm. Now by using I got 45 cm, I got 45 mm. By using rigidity criteria, I got say some 50 mm. It means to say that my shaft is stronger enough to withstand the shear strength, but is weaker in rigidity. That is, it is undergoing the higher deformation. So I have to take the maximum dimension. That is, I have to take diameter D should be equal to 50 mm, which are the maximum dimension I have to take, because 45 mm is good enough to withstand the shear strength, but it may not be able to withstand the deformation 50 mm, that deformation. For not to withstand the deformation, I require shaft of 50 mm diameter. So I am which of the maximum dimension I am taking it 50 mm. This is the design concept. Next, when I talk about shaft, we talk about power. Power is given by power. Power is equal to 2 pi nt. This is mean torque by 60. Because when you take an engine, this is torque T, this is theta angle, suction stroke, say compression stroke, expansion stroke, and exhaust stroke. For all the strokes except expansion stroke, this is suction, this is compression, this is expansion, this is exhaust. For all the stroke, yes, except as the expansion, there is only energy released at the expansion stroke T max. But for all this other stroke, the energy is given by, there is something called as mean torque. This energy is given by the flywheel, which absorbs the energy during expansion and gives the energy for the rest of the stroke. This other stroke. So when I take the mean of this is mean torque. This is mean torque. So in case of shaft also, even there is a maximum torque available, but in the power expression, you are using this T mean torque, T mean. Okay, and power is in watts, that is Newton meter per second. N is in RPM. T mean torque, this torque, which is in Newton mm. I will always take it as Newton Newton mm. The power is in watts. Newton. There will be Newton mm per second only because T is in this one uh, Newton mm. This will be Newton per second. Okay, kilowatt per second. Okay, or watt per second, and then uh, torsion equation T by J is equal to tau by R is equal to G theta by L T Newton J moment of inertia, polar moment of inertia, power 4, tau Newton per square, radius r rigidity modulus G Newton per square, theta it will be given in degrees for x degree, x into pi by 180 radians we should do. It is radians in we should keep it in length L in mm. Now these all things we should keep in mind. Okay. Next, sign convention will talk. Sign convention. for- Give me a moment. Okay. So when I take now, this is my shaft. These are my four fingers. This is my thumb. Okay. Now I am applying a torque like this. I have to bend my four fingers in the direction of torque like this. See how I am bending in the direction of these four fingers. I have to bend in the direction of torque. Then thumb gives the axis. This is the axis. If you bend your four fingers in like this, okay, then your thumb gives the axis which is in the x direction. Then this is the direction of torque T. Now, in this case, in the right hand side torque, if you apply torque at one end, there will be reaction torque at the other end. So, assume that this is like this. Bend your four fingers in the direction of torque like this. Okay, and then your this will be at give me a moment. ಏನು ಹೇಳಿದ್ರಿ? Now, this is the reaction torque. This is the reaction torque. Now, if you bend your four fingers in the direction of torque like this, your thumb will be pointing like this. This is the torque. This is your positive torque sign convention. Positive torque sign convention. I will give a clear crystal picture of this, but time being wait. Negative torque in the sense my torque will be the torque will be like this at this end. Therefore, if you hold your four fingers in the direction of torque, your axis will be like this. The thumb gives the axis, this will be like this. And at this end, this will be like this. Therefore, towards the cross section, this is negative. Away from the cross section, there is positive torque, negative torque. But generally, what we'll do is to avoid confusion. What we'll do is, for example, if this is the shaft, this is the shaft, and this is the say length or x dimension 0 to say some 7000 mm is the torque length. So what is the assumption is in the direction in the direction in the direction in the direction of length in the direction of length counterclockwise torque is positive in the direction of length whichever there is a counter. This is the assume this is the clock, this is 12 o'clock, 3 o'clock, 6 o'clock. If you take this cross section like this, in the direction of length counterclockwise torque is positive. So if there is a torque like this, if there is a torque like this clockwise torque, this is T1, this is T2. Therefore T1 is in clockwise direction, this is minus T1, and T2 is in counterclockwise direction, this is positive T2. Okay, since there is a confusion, you acting like this is also positive, it will lead to confusion. The best way is in the direction of length counterclockwise torque is positive, that you should remember. For example, a shaft might be given like this, and you will ask to analyze. Sometimes you will give the shaft like this, shaft like this. Okay, in this case, in this case length is 0, 0 to L is this. In the direction of length, this is length x or length L. In this case, length x, this is your 0, 0, this is your x. So in the direction of length, it should be positive. When you solve the problem, we'll come to know. In this case, if this is positive, this is a positive t, positive t. In this case, in the direction of torque, counterclockwise torque is positive. But you can see this. If you take this is like this is clockwise. In this case, this is clockwise. This is acting in, this is also acting in which direction it is acting. If you curve your fingers, this is counterclockwise turn, counterclockwise turn, minus t, this is minus t. We'll solve this problem, we'll come to know. But time being, the sign convention is in the direction of length of the shaft, in the direction of length of the shaft, in the direction of length of the shaft, counterclockwise torque is positive. That's all you should remember. When you go to the problem, automatically will solve this. You will come to know. This is positive torque, this is negative torque. Hope you understood this. Okay. Next, when I come to the step to shaft, I will discuss that. Any doubts until here? Any doubts? Any doubts?
No, sir.
Okay, shall I stop at this point? Afternoon we'll be having lab as usual. We'll do that ISO and chapter and two more experiments will conduct. Okay. Machine shop will also follow parallelly. After this class or after 1 or 2 days, it may follow. You follow up with that respective changes. You ask Shantala Madam regarding machine shop. Empty lab I will take in care of that. Okay. I'll stop at this point. Thank you.